Good morning, ladies and gentlemen. What I'm going to talk about here covers about 15 years of my research. Most of you won't know it, but I published the first paper on it in 1997 while I was still an undergraduate student here in Vienna. And the last one was published last year while I'm now a professor in Liverpool. Now, there was a slight gap in the publications between 2001 and 2010 where I didn't publish anything. And the reason was I couldn't explain why an electron changes its wavelength when it changes its velocity. And I felt if I can't explain that, then I probably don't know what electrons are and do, and then I have no chance of understanding quantum mechanics. And that changed only with a PhD student who incidentally submitted his thesis last Monday. And he came into my office and asked me, why didn't you publish anything further? And I said, well, I can't explain that. But then I thought about it, and half a year later I had an answer, which I think actually makes sense. So this is the story, more or less. The overview is I will sort of show you the problem. Then I will sort of talk about densities and wave functions. And I will keep that very brief so I don't go into technicalities. You have to look that up in my publications. Then I will talk mainly about processes and experiments. The first one I'm going to look at is acceleration of electrons, Stern-Gerlach experiments, double-slit interferometry, where I have some suggestions for my experimental colleagues here. And the last one will be Bell-type experiments. And then I'll talk about something, the last 5 minutes, if Gregor reminds me, which I've done in the last 2 years. So I've thought about extending the model to atomic nuclei. Okay, so where's the problem? This is the problem. We've heard that on the first evening. You can sort of devise other ways to find that this is really problematic. And then, of course, all the implications we have from there are also becoming sort of slightly untenable, so that electrons are point particles, that the electrostatic energy is infinite, that wave functions do not have a physical reality, and that measurements cannot be arbitrarily precise. I will show in the following that this one is actually not correct, and therefore this one is probably also not correct. Then all the implications we have here are probably untenable as well. So let's see why this is. Then let me introduce you to what I do in my day job. In my day job, I simulate scanning probe microscopy, which is, I think, one of the great scientific inventions of the 20th century. It was invented by two Swiss guys, Gerd Binnig and Heini Rohrer, in 1982. In the first experiments in 1982, we could just see gold terraces, and the resolution was about 1 nanometer, temperature is 300 Kelvin. Then 5 years later, people in the United States improved on the method. They could now see single gold atoms on the surface, again at room temperature, resolution 0.3 nanometers. In 1993, IBM Almaden near San Francisco, they came up with low temperature scanning tunneling microscopes. These here are individual silver atoms. This is a silver surface. And these wave patterns you see here is the silver surface state at 5 Kelvin, and the resolution here, the vertical one, is about 1 picometer. In 1999, they developed a single molecule spectroscopy, so they could actually measure if a single molecule gets vibrationally excited. This was done in Wilson-Ho's group. The energy resolution in the experiments was then down to about 10 milli-electron volts. The temperature is 4 Kelvin. In 2004, in Almaden again, they measured single spin-flipping excitations of electrons. The resolution here is 0.1 picometer. The energy resolution is 0.1 milli-electron volts, and the temperature is 1 Kelvin. And the last example I give you is they measured in 2008 the force it takes to push a single atom from one position to another one on a surface. And here the energy resolution is 0.1 milli-electron volt. The vertical resolution is 0.1 picometers. Horizontal resolution about 10 picometers, and the temperature is 0.5 K. The best instruments today reach a limit of 20 millikelvin, and they are extremely precise. So why is this a problem? Okay, what they measure is the two-dimensional distribution of the density of electron charge. Why is this a problem? Well, let's look at it in detail. Here's a silver surface with a quantum coral. You see here this standing wave pattern. You also see here the position of the surface atoms. Here are the numbers. The temperature is 5 K. Distance of atoms, 290 picometers. Wigner-Seitz radius, which gives you the radius of a sphere where one electron is in this sphere, is 106 picometers, so it has to do with the density. The band energy is 80 milli-electron volts. The maximum energy you can have, therefore, is also 80 milli-electron volts. The lateral resolution is 20 picometers, and the vertical position is 0.05 picometers. So if we look at the maximum energy and the local uncertainty, we can derive that from the Heisenberg uncertainty relations. The delta P is a maximum of 1.53 times 10 to the minus 25 kilogram meter per second. So the delta X is a minimum of 348 picometers. Now, if you do a statistical distribution of point-like electrons measured on such a surface, what you get for 100 electrons is this one on the left, for 1,000 electrons, this one in the middle, and 10,000, this one on the right. If we calculate now the standard deviation in these measurements, it's about 300 picometers, which you would expect. And that can be compared to the resolution in the experiments, which I do on this slide. So we use the standard deviation, which is defined here. The maximum standard deviation can be inferred from the position of an experiment and the feature height. So the feature height is at least 30 picometers. The position is 0.1 picometer, which gives you something below 0.3%. And that means essentially that 99.7% of all the measurements of this feature height must be within a certain radius, and the radius is defined by 3 times the standard deviation. And this must be then smaller than the delta X. If we then look at the results for the surface-state electrons on silver, we find that the delta X is about 10 picometers, the 3 sigma is about 800 picometers, and we find that the delta X is much smaller than 3 sigmas. So there's a clear contradiction. You can play it in 2 other ways, and the contradiction is always 2 orders of magnitude. So that means essentially the following. If we assume that the electron is a point particle, if the uncertainty of location is related to the uncertainty of energy and momentum, we find that the standard deviation in experiments is only about 1% of the theoretical value. And the uncertainty of location corresponds to an energy value of 1,000 electron volts. And the conclusion we can draw from that is that the electron is not a point particle, and the uncertainty relations are violated by thousands of measurements every single day. Okay? So this is the conclusion. Now, this leaves us in something of a problem, because the uncertainty relations, together with the point particle electron, actually define operator mechanics. So we can't really use it, because the logical foundation, this is what this says, is actually not tenable. So how do we go from there? This is the publication last year. Well, we come back to Vienna. That's what I've done here. And we remember 2 great sons of this city. One is, on the left, is Erwin Schrödinger. He was born here in 1887. And the one on the right is Walter Kohn. He was born here in 1923. One invented or found the wave equation of electrons. The other one invented density functional theory. Who has heard of Walter Kohn? Let me check. Okay, the majority. Let me give you a context here. We have a big computational center in Edinburgh in the UK, and they have about 20,000 cores. And from all, this is for all of science and engineering, and from all the calculations done, 50% are density functional theory calculations. So it's massive, okay? Now, so what do they say? Schrödinger said a system is fully defined by its wave functions of electrons, and Walter Kohn said a system is fully defined by its density of electron charge. And if you combine those 2, you get a completely new theory, as I show you in the following. Now, Andre wanted a principle. Here is one principle. It is the density of electrons is a real physical variable. That's all you need, and then you can derive everything else. So how do you do that? First, you start with charge density waves. These are plane waves in one direction, in the z direction. The limit is well behaved, so if you go to 0 velocities, then basically you get inertial mass distributions, and you only get wave-like features if the electron moves. If you do that, then you have to introduce additional components. I introduce them as vector components, linking them to electromagnetics, sort of, but it's not necessary. All you need is 2 vector quantities, which are perpendicular to the direction of motion. I call them spin components. You will find out in a minute why I do that. And these are necessary consequences of energy variations of the density components, because you need a reservoir to actually make up for the differences. Okay, so this is basically where we start. And this is all published in this paper, which is rather lengthy and technically complicated. So I presented this paper in a talk in Vechio last year. And people told me afterwards it was very demanding, so I skipped most of it today. If you want to read up the technicalities, they are in there. Okay, so how do we go from there to wave functions? Basically, we say that the spin component now is a product of these 2 vector components. In geometric algebra, a product of 2 frame vectors is actually a 3rd vector times the imaginary component. So then we can write the spin component in this particular way. Then we define a general wave function as a square root of the density plus this square root of the spin component. And we have then essentially as a number plus, this is in geometric algebra, a bivector, and it can be written in this way. So it's a vector in the direction of motion, either plus or minus, if we go to the complex conjugate, or if we change the direction of the fields. And those two, this one times that one, actually obey the Born rule. They give you a constant, and it's the inertial mass density of the electron. We can simplify that somewhat by saying, okay, this vector is actually a hidden variable. Then we arrive at the plane wave description for the free electron, and we are home and dry because this is what the Schrödinger equation describes for free electrons. We can then introduce potentials, and we can introduce vector potentials, and then we get the general form of the Schrödinger equation for this one. It's all in this paper if you want to look it up. The important things here is that the group velocity is equal to the velocity of the electron, which is exactly what we have in quantum mechanics. The frequency of the wave is proportional to the kinetic energy, which is also what we have in quantum mechanics. And the interesting one is the third one. The total energy is the energy of its inertial mass, which leads us back to classical mechanics. So, since in my day job I'm a theoretical condensed matter physicist, I looked at ways to actually use this to do many-body physics, and here is how we can do that. If we have a general wave function like that, then we need to introduce an additional potential, a bivector potential, into the Schrödinger equation to get the actual chemical potentials which are constant, which then leads to two coupled equations which describe your many-body system. So this is the many-body interactions, and you have this system is an equation for the charge with some source term, and this one is an equation for the spin component. It's a vector equation, again with some source term. So these two equations should completely describe a many-body system, and the big advantage here is that the many-body wave function in this case has only 4 instead of 3n variables. So it's much easier to solve, and it can actually lead to a linear scaling formalism of density functional theory. Okay, so this is all I tell you about the formalism. Now let's go to actual experiments. What happens, processes and experiments, what happens if something else happens? So for example, what happens if an electron accelerates? Then what will happen is its velocity will change, the density distribution will change, the field components will change, and the external field will also change. How is that described? By this one here, which you could call a local Ehrenfest theorem, because it's essentially the classical formulation. But underneath the classical formulation happens something else. These two together, in the time variation give you 0, but if one changes, if this one becomes smaller, then this one becomes larger, and that tells you that the wavelength changes because you shift energy components from the mass component into the spin component. This is what happens if you accelerate, and this is why the wavelength changes. So this would be the answer to my student today. The next one, we heard that also to create length, is Stern-Gerlach experiments. If you solve with this framework the hydrogen problem, what you obtain is two solutions. The spin is parallel to the radial vector, either outward or inward directed. And if you sort of have a free electron, then you recover the classical equation for Lorentz forces, of course, like we had before. But if it's not free, then you have a rotation of the spin directions. This is what happens here. So you have an induced spin component, which is either parallel or anti-parallel to the field. This leads to rotations around the field vector and to a magnetic moment, which is induced into this hydrogen electron, which is then either upward or downward, and leads to two separate variations of the trajectory, either up or down. So you have two solutions, which is exactly what you observe in the experiments. Now, the difference here is in the standard model, you say the spin is isotropic, which is also here. The measurement breaks the spin isotropy. That's what you have in quantum mechanics. And there's no process to explain the symmetry breaking. And here we have the spin is isotropic. The measurement induces spin components aligned to the field. And the measurement measures the induced spin components because all the other ones cancel out. How am I doing with time? 7 minutes. Well, I think I might just do it. Okay, the second experiment, we've heard a lot about double slits. And so let me remind you what Feynman path integrals will give you. You have a single particle, Then at some point, you have vertical particles. Every vertical particle goes to one slit. And then at some point, after the slit, they recombine, and you find one impact on the detector stream. Now, the problem is, of course, there's no physical process known which could account for the creation of virtual particles and the recombination after the interferometer. We just don't have such a process. So why should it happen? Well, we heard that there are other solutions existing. I will give you a tentative solution, which I think our experimenters here could actually pick up. Now, this model is due to Duane and Lande. And what they basically said is you have single wavelets of particles. They interact with the slit system. But since the slit system is an atomic system, it has a discrete interaction spectrum, which allows the particles only to acquire a discrete lateral momentum. And this is what you observe on the screen. So you observe discrete impacts. And then, if you have thermal broadening, you basically observe a Gaussian width of these single impacts, and then you observe the wave-like interference pattern. So there could be an experimental test here. And the experimental test is actually quite simple. All you need to do is you need to freeze your system down to 4 Kelvin, say, helium temperatures. And then what you should observe is actually this one. And then if you go up with the temperature, it should gradually evolve into that one. So my prescription would be perform interference experiments on these systems in UHV, should be doable with photons and electrons alike, and perform them at 4 Kelvin. And I'm pretty sure we can do that with our methods in condensed matter physics. We can calculate the vibrational and the phonon excitation spectrum of your slit system, and from that you should actually get the discrete deflections. Okay, so this is my suggestion. And the slit environment is composed of atoms in a regular crystal lattice. Such a system always has discrete interaction spectrum depending on the chemical element and the crystal symmetry. I think actually, now let's go back to Vienna. This was already established here in Vienna on a rather larger system on C60 molecules, and the Zeilinger group published it in 1999. What they claimed is basically that C60 molecules have a wavelength, and that they observed this in these experiments. Now, for me, as a condensed matter theorist, that is a problem, because students of mine and quite a few colleagues have calculated this system. We know everything about it. We know the position of the atoms to 1 picometer. We know the charge density distribution to the factor of 10 to the minus 6 because we can measure it. We know the vibrational spectrum because we can also measure it. We even know the light spectrum, emission and absorption of this particular molecule. But we do not know, because it is not in density functional theory, we do not know the Breuil wavelength of this molecule. So this is something which doesn't show up in our calculations. So where is it? Well, actually, another group in 2007 did a clever new experiment. So they said, well, we know that this molecule is polarizable. If it is polarizable, then basically it could be that the interference fringes come from the interaction of the dipole moment of the molecule and the slit system. And so they put an electric field before the slit system and could show that really if they change this electric field, they change the dipole moment of the molecule, and then they change the interference fringes. So for me, this is an experimental proof that what happens is actually the interaction between the molecule and the slit system creates these interference patterns. So the last experiments I want to talk about is these aspect type experiments. Basically, I agree with Theo that Bell inequalities are not relevant for locality, but I still think we need a model to explain this experience. We need to know what's going on. And what I do here is I develop a new model based on a geometric algebra where I simulate 2 photons coming from a common source and having some sort of phase differences. So I have, at this point and at that point, I have a rotation and a filtering. The rotation is a rotation of the field vector, which is in direction E3 or minus E3, which gives us then in the exponent complex numbers. If you have 2 rotations, then you have to multiply the rotations, and the filtering then takes care of it that it's only a real number. So then the coincidences agree completely with the CSHS formulation. So for the C++ and C minus, you get cosine squared of the angular differences, and C plus minus is 1 minus. And the expectation value agrees also very well with what Aspect found in 1982. So the polarizer is this one. Now, if you have 4 particular angles, then the S value is 2 times the square root of 2, which is also exactly what you find in quantum mechanics. But in this case, you find it in a strictly local model. And all you need to think of is complex phases and rotation in three-dimensional space. Now, where did Bell go wrong? Well, the problem is here. He thought he could describe the probability by a product of 2 real numbers. If you have 2 rotations like that, then you have a complex number. You can never decompose this complex number in this particular way. So I agree with you. It's just simply not right. This was published last year. Okay, so last part. This is something I haven't published yet, but I think it looks very promising. So the question you have is, if electrons are extended particles, and if we know that neutrons basically decay into protons and electrons, what does an electron do in a neutron? Okay, so you can sort of look up experimental data, and you find that from scattering experiments in 1961, that neutrons have a positive core and a negative shell. We know that they decay into a proton and an electron, and that there's an excess energy of 0.782 mega electron volt. So the first problem you have is actually understanding why the neutron is heavier. Well, you can sort of look at that from a field perspective. And, okay, so the question is there a high-density phase of electrons in a nucleus? If you look at the energetics, and if you think of the electrostatic field, then an electrostatic field of a hydrogen electron has an energy content of 11 electron volts. But the electrostatic field of a neutron electron, assuming that the neutron is 1.5 Fermi across, has about 1 mega electron volt. So from the electrostatic field component alone, you could actually understand why the neutron is heavier. So then, with this sort of information, you try to construct a solution. You use the Schrödinger equation like you do for the hydrogen. We know from the hydrogen solution that we have exponentially decaying densities and wave functions. We know from the characteristic equation that we only find a solution if this is 0. From that, we get the decay length, and it depends on fundamental constants. And, okay, the length scales and the energy scales for the hydrogen are actually defined by the Planck constant. So this gives you that. And now, if you think that we have a nuclear environment, that maybe this changes, then we can say we have a constant for the nuclear environment, which is x times the constant for the atomic environment, which changes the decay constant. It changes the decay constant here. It also changes the fundamental length, and it also changes the fundamental energy. So far, so good. So the decay length, the unit of length, and the unit of energy all scale differently in a nuclear environment. Now we solve the Schrödinger equation in nuclear units, and then we find for the total energy this expression here, which depends on the nuclear radius and on this x factor which we introduced up here. The nuclear radius we know actually from the scattering experiments. So then we find for the x, the 1 over 18,779, which is exactly equal to the fine structure constant. And this one is an experimental value. I didn't make this up, I just took it from experiments. So alpha is equal to the scaling factor in nuclear units in this model. Then we can look at the energy values, and the energy unit, interestingly, is equal to the rest energy of the electron. And then we can sort of think about energetics. So we have a metastable state. That its metastable comes from the eigenstate, which is negative. Then we have a transition state, and then we go to the ground state. So what I cannot explain at the moment is why we have 800 seconds until this decays into that. I don't know. But I think that there's scope for working on it. Now, if you think of that, then you also think of general nuclei, and then you can actually develop a shell model. So if you think that nuclei are composed of protons and electrons, then protons are immersed in negative charge. And then the ground state solution is that the interproton distances are equal. Then for shell 1, you get to helium. Shell 2, you get to oxygen. 3 to silicon, 4 to argon, and so on and so forth. So you naturally actually recover what is known in nuclear physics as the magic numbers. And I think with this sort of concept, we could actually do nuclear physics in the same way you do density functional theory. And that's something I would very much like to work on. If anybody of you is interested, I'd be happy to discuss it. Okay, 6 things to remember. The first of all is the uncertainty relations are violated by up to 2 orders of magnitude in thousands of experiments today. So it's not one experiment, it's every day, it's thousands every day. Wave functions themselves are not real. but the components, mass and spin density, are real. Rotations in space generate complex numbers, which are not described in the Gibbs vector algebra. This is where we usually go wrong when we try to think of three-dimensional space. So we have to do it in geometric algebra. Double-slit interference experiments most likely show two features: a discrete interaction spectrum with the slit system and a thermal broadening due to environmental conditions. If we in our experiments can decouple those two, then we can actually find out what is really going on in your interferometer. And based on the experimental neutron radius, we are led to conclude that the fine structure constant describes the nuclear energy scale, and closed shell nuclei could be due to the geometrical arrangement of nuclear protons. And finally, three things I've learned. Mathematics is not physics. Mathematical models should be sound, based on sound understanding of physical processes, which I think is what we didn't do in the past. And a proper mathematician will always invent a new reality if it contradicts his theorems. So beware, but they're just like that. Second one, it's easy to come up with complicated models. It's much more difficult to develop simple ones. And the third one is, if it's weird, it's probably wrong. Thank you very much.